Hello, chemists. One more time, let's talk about kinetics. This is going to tie together the whole chapter just so that you can see how all the parts are related. So I'm going to go back to that example that I already have written. Nope, not right there. The example that I already have written at the end of the notes. Okay, so just a generic practice example. What can we find right now? We can find the rate of reaction equation. All right, why are we finding that? Number one, if you want to compare the reactants to each other or products, then you need an equation that takes that into account. And I call that, remember, the reaction rate equation or the rate of reaction equation. Rate is rate is rate. Rate means the change in the concentration over the change in time. So the word rate, it doesn't matter what equation it's written in, means the same thing. It could be at different times and different concentrations, but the word still means the change in concentration over the change in time. So if you want the rate of reaction equation, remember, write the word rate equals, and then you're going to do each of the pieces, and I'm going to put a couple numbers in here so it's more interesting. All right, the rate, these are reactants, so it's a negative change in A over the change in T, and then we're going to take into account its coefficient, and it goes on the bottom. B is also a reactant, so that's the only reason I'm putting negative. Remember, rates are never negative. It just means being used up. Over the change in T, and its coefficient happens to be 1, equals, this is positive because it's a product, over delta T, but it's appearing 3 times as fast. And D, which coefficient is 1. So that is used if you want to compare the reactants together. If you want to compare the rate versus the concentration, you are going to use the rate law. You're going to use the rate law. And it only uses reactants. And remember, you have to find it experimentally. So you do not use the exponents. So that's what I would call the generic. All right, why do I want that? Because it gives me a connection between rate and concentration. And remember, and you don't have to put the word law there. That's just a visual. So that is the rate law. What are you going to get? You're going to find the orders, and you're also going to find this new thing called a rate constant. Okay, so I'm going to put that under number 3. If you need to find the orders and the constant, well, what are we going to do? Well, one way is experimental data. And if you have concentrations and rate, that's just the algebra that we've done in the past. So we're not going to do the algebra for this again, but you'd put these two together, and these go away, and so then you'd have those to the x, so forth and so on. Okay. All right. Well, what if I don't want concentration versus time? What if I want, sorry, time, rate versus concentration? What if I want concentration versus time? A little more useful in a laboratory setting. All right, that's when you have to get the linear equations. Okay, so that's not on here. So this is the old stuff. I'm going to go over to the whiteboard now. Well, I might have room right here. All right, so the linear equations. The power of the linear equation is it will give you concentration versus time. And if you have the data, it will also give you the order and the K value. So that's 2 ways to find the orders and the K value. All right. If you graph concentration versus time and you get a linear line, that is zero order. Hey, math, if I graph concentration versus time and I get a straight line, I am telling me what? That I am zero order. If I graph natural log of concentration versus time and I get a linear line, I'm telling you, oh, you're first order. Now, I do have to be careful when I'm doing the linear equations. It's always just one reactant. It gets too complicated to show you more. So this is just one reactant. So it's zero order or first order. Hey, math, if you do 1 over the concentration versus time, and remember this is a positive slope, hey, I'm second order. No sig figs off of graphs, and you have to plug in the units. Right, that is the purpose. You are going to find the order and you are going to find the K value. So just like before, it is another way to find this one, but its equation will now relate concentration versus time. All right, well, can I find the activation energy off of this graph? Change colors. All right, big question. Can I find the activation energy from anything I have? No. Okay, the activation energy cannot be found on any of these. You have to have a different graph that includes temperature. And now I will go over to the whiteboard. If you want activation energy, you have to do its linear equation called the Arrhenius equation. So 1, the rate of reaction, 2, the rate law, 3, the linear, 4, the Arrhenius, these two will tell you K and the orders. Rate law is rate versus concentration. Linear is concentration versus time. And Arrhenius is the natural log of K versus 1 over the temperature. All right. Can you get the order and the K off of the Arrhenius equation? Remember, K is what we plugged in to get the Arrhenius equation, so we already know those. All right. What else did we learn? Now, of course, there's catalysts and everything, but the last thing we did was mechanisms. Mechanisms, remember, are the elementary steps that we know exactly what is happening, and so the coefficient is also the order. Yeah. All right, so if I told you this one was concentration, 1 over concentration, and natural log of concentration, you can put them all on the same graph versus time, and then you would ask the computer or your calculator or figure it out yourself. You would need the slope and the intercept. All right, I know that seemed awfully simplistic, but in a nutshell, that's what you're supposed to tie together for kinetics. All right, until next time, jolly out.